Couple things before, well, one thing before we get started. So your last in-class exam, because of course there's the final after that, is coming up next week, so the 19th. I'm not exactly sure what it's exactly how much it's going to cover yet, because I need to figure out how much we're going to cover. But on hopefully Friday, if not over the weekend or very, very early on Monday, you'll have the review stuff out for that. For you to look over before Thursday. But so it'll definitely be covering the chapter 4 stuff that we're going over right now. I don't know how much of chapter 4 we'll get through. There will be a tiny bit of chapter 3 on there. As I mentioned before, there's not going to be any induction, but there is that recursive data structure section, the 3.5. So remember, recursion is different than induction. So there won't be any induction proofs, but I can ask you some recursive data structure stuff like the last quiz we just took. So 3.5 will still be fair game, even though it's recursion. There just won't be any induction. So I won't ask you to prove that things work. I'll just ask you to use them, that kind of thing. And then there will be this chapter 4 stuff on counting is kind of what it's classified as. But anyway, I'll talk about that a bit more as we get there. I'll have a better idea either on Thursday or Tuesday at the latest of exactly how, well, no, I'll probably figure it out by Thursday because I'll get that stuff out to you as soon as possible. Anyway, I'll tell you more about that one now. So remember, we're going over 4.1. We're pretty much done. We just have kind of one last example. And so we had kind of these two different rules. We had the kind of multiplication principle that said if we have two or more sets and we essentially want to choose a set of things out of these sets, we can just multiply the cardinalities of the sets together. And then remember, there was also the addition principle before that, which essentially said if the sets are disjoint, which remember that means that if we intersect the sets, it has to be the empty sets, but they can't share any elements. But if the joints are the sets are disjoint, and we want to figure out how many, things we have between them, we can just add up all of their cardinalities. There are a few situations where we can actually use both. And so that's like the last piece we have to talk about in 4.1 before we move on to 4.2. So say I wanted to figure out how many non-empty strings of at most 3 letters can be formed from a 26-letter alphabet. So at the very end of Thursday before our quiz, we talked about 3-letter strings on 26-letter alphabet in general, and then if we can't repeat things. So this one seems very similar to those two, but note the wording here includes at most 3 letters. So we could also only have 1 letter, or we could have 2 letters. So we need to take into consideration kind of all of those different types of strings. So, and those are kind of disjoint sets. So we have 1-letter strings. So if we figure out how many 1-letter strings we can have, well, you only need 1 letter and you've got 26 choices. So there's 26 choices for a 1-letter string of things. If we're going to have a 2-letter string, and we're allowed to repeat things here, so we have essentially 26 choices for each piece of the string. So if it's a 2-letter string, we'll have 26 times 26. And then for the 3-letter string, we have 3, sorry, I was saying 3, so I wrote 3. We have 3 spaces we need to fill, but there's 26 choices for each of them. So there are 26, essentially 26 cubed 3-letter strings that we could form. So if we want to know how many strings of at most 3 letters, since these are disjoint sets, there's no 3-letter string that's also 1 letter. There's no 2-letter strings that's also 1 letter. So since those are disjoint sets, we can essentially say, well, then the total amount of strings we would have in this situation is going to be 26 plus essentially 26 squared, if I can write it like that to save myself a little bit of space, plus 26 cubed. So essentially, it's kind of a mixture of both the multiplication and the addition principles. We had to use the multiplication principles to kind of get our disjoint options, and then since they were disjoint, we could just add them together. So if we want to know how many non-empty strings of at most 3 letters there are for a 26-letter alphabet, it's 18,278. That sounds really low. I'm going to trust and believe, but Let me double check. Yeah, no, it's just not as many as I thought there were. I thought it was going to get much larger than that. No, that's right. So here, again, we kind of had to mix the two. We had to find each of the separate cases using the multiplication principle, and then we could add them all together since they don't share any elements. So in that example we just did, as I've kind of already said multiple times, we had to use the multiplication to determine the possible strings, and then we could add them together. So I've said that multiple times already. I'm going to wait like 5 seconds. Anybody has a question on that before we do the last one in 4.1? Okay. I actually want you guys to think about this before I write the answer down. So I'm going to sit in awkward silence for like a minute and a half while you think about the answer to this one. So Illinois license plates used to consist of either 3 letters followed by 3 digits or 2 letters followed by 4 digits. How many plates are possible? So I want you to try to figure out the number of plates that are possible. I'm going to sit in awkward silence for a minute while you do that. Okay, so there's the 2 choices. You either have 3 letters, 3 digits, or 2 letters, 4 digits. So in the 3 letters, 3 digit case, you essentially have 6 spaces to fill. The first 3, you have essentially 26 choices for each, because it didn't say that we can't repeat the things. And then since there are 10 digits, the last 3 spaces would have 10 options each. And then for the 2 letters, you would have 26 times 26, and then 10 times 10 times 10 times 10. And again, since these are disjoint sets, there's no plate that has 3 letters and 3 digits that also has 2 letters and 4 digits. We can just add these results together. You can find the results separately. I'm going to just write the total down before the total calculation down. I'm going to write it as 26 cubed times 10 cubed plus 26 squared times 10 to the 4th, just to save myself a little bit of space. And so if you calculate that total, or if you calculated the total of the 2 pieces separately and then add them together, you should get 24,336,080. There it is. Let me just check it really quick, because I'm just trust and believing my notes, but sometimes my notes are wrong. Oh wait, I'm not getting 80. I probably just miswrote that in my notes. I'm getting 24,336,000 just themselves, which makes more sense. But anyway. Questions, concerns on that before we move over to 4.2, or anything from 4.1 that you want to talk about really quick before we go over to 4.2? I'll wait a couple seconds in case someone's typing something. So 4-2, it's kind of similar to 4-1, so I don't want you to think that they're like completely disjoint situations, but there's a little bit more structure to what we're going to do in 4-2. So 4-2 is on stuff called selections and arrangements. Sorry, I just remembered something. Okay, so first we're going to talk about something called permutations, which also are related to arrangements. So when we think about arranging physical objects, you think about the placement relative to each other. So we can kind of also talk about that in terms of mathematical objects, and sometimes the order is going to matter, and then other times the order is not going to matter. But say we wanted to find all the different ways to list the digits 1, 2, and 3 using all of those digits only once. So you could think about it in the way we were kind of just doing it, where you have 3 choices for the first, 2 choices for the second, 1 choice for the last one, so 3 times 2 times 1. If I want to write down the very last decision tree I will ever draw, I know I already said that I wasn't going to draw any more of these, but I'm going to draw one last one. So if we think about this as kind of a tree, and it would specifically be called a decision tree, you know, we can decide which digit to use. And then after we pick the first one, we only have 2 choices for the second one, and then only 1 choice for the last one. So our decision tree would look like this. And of course, that also gets us 1, 2, 3, 4, 5, 6 choices. So we have 6 ways. So we could also, again, think of this as 3 times 2 times 1. You have 3 choices for the first digit, 2 choices for the second digit, 1 choice for the third digit. So we have 6 ways to kind of arrange these. Now notice that the order also mattered here. So 1, 2, 3 is not the same as 3, 2, 1. Now in math, a list, so I didn't write out the list. Let me write out the list. So we had 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1 are kind of the choices if I write them out in a list. So each of the lists that I just wrote down is called a permutation. And a permutation is a rearrangement of all elements in a set into some order. So we essentially had the set of the numbers 1, 2, and 3, and if I rearrange them into any particular order, that would be a permutation. So absolutely each one of those ways I can write those digits is considered to be a permutation. So in that example we just looked at, we had 3 elements that we were arranging, 1, 2, and 3. We had, as I've kind of already said, 3 choices for the first, but once we made that choice, we only had choices left, and then we only had 1 choice left for the last item. So we found that the multiplication principle essentially gave us that it was 3 times 2 times 1, which gave us the 6 ways. Maybe I shouldn't write ways in there because it'll make it not make sense. So we had 6 permutations on those digits. And what we're going to kind of do is we're going to expand a little bit on that multiplication principle. So notice here we were 3, 2, 1. But then what if I think about how many different 3-letter strings can be formed on a 26-letter alphabet if no letter can be repeated? So we've been talking about 3-letter strings a lot. But if I can repeat absolutely no letter, so they all have to be 3 completely different letters, how many different ways can I do that? Well, in my first blank, I essentially have 26 choices because I can use any letter I want. But then with the second blank, I only have 25 choices because now I can't let it be the same one as the first one. And then for the third blank, I only have 24 choices because I can't let it be the same as either of the first 2. So that would be 15,600 if you're curious. That's not really the point here, but. So we have 26 times 25 times 24. And notice in the other one we were doing 3 times 2 times 1. So it's kind of like it's going downwards, nudge, nudge, wink, wink. So in section 3.1, remember we defined the factorial function, which is represented by a exclamation point. So if we have n factorial, remember that's essentially n times n minus 1 times n minus 2 all the way down to get to 2 times 1. And that only works for non-negative integers. And by convention, Remember we said that 0 factorial was 1. So in example 1, the number of permutations that we were actually looking at on 1, 2, and 3 actually turned out to be 3 factorial because it was 3 times 2 times 1. Now in that second example that we just did with the 3-letter string, there were 26 times 25 times 24, which is not a full factorial, but is there a way that we can express it in terms of a factorial, or maybe multiple factorials? So if we think about this a little bit, if we have 26 factorial, well, that's 26 times 25 times 24, and so on, times 2 times 1. That's, you know, way too many. So this is too much, obviously. And notice that essentially, let me actually do one last thing to try to make this the tiniest bit clearer for the next thing I'm going to do. Let me write times 23 and then do my little dot, dot, dot. But kind of if you think about how much we don't want in that 26 factorial, it's essentially this, you know, kind of back, you know, 3/4, that back piece we don't want. So we essentially don't want that 23 times 22 times 21 all the way down to 2 times 1. But that's 23 factorial. So we can actually represent 26 times 25 times 24. And I have a point to this. It's not trying to be silly about it. 26 factorial divided by 23 factorial, right? It might seem a little silly to do so at this point, but I'm building up to a definition. But I can technically, that does represent 26 times 25 times 24, because the top would be 26 and 25 all the way down to 2 times 1, and then we're dividing by 23 times 22 all the way down to 2 times 1, so most of the things cancel out, and the only thing we're left with is 26 times 25 times 24. So this essentially, question so far? We've kind of, again, it's very much related to 4.1, but if you have a question, let me know. So this kind of leads us into this thing called the arrangement principle. So the number of ways to form an ordered list of R distinct elements drawn from a set of N elements. So you're starting with a set of N things and you're only taking R of them. So in the last example, we had 26 letters, we were only taking 3 of them. This is going to be represented as P of N comma R. There's no good real way to read that I know of. Sometimes I'll call it permutation of N and R elements, but essentially this is equal to N times N minus 1 times N minus 2 all the way down to N minus R plus 1. Now I know that's really generic, but essentially if you think about it, we were taking 3 elements in the last one, so we essentially had to take 26 times 25 times 24, so it was essentially 26 minus, we're going 3 elements long, but we only wanted to go down to 24, so if you think about it in terms of the numbers that we just did, it does make sense. We can also think about this as N factorial over N minus R factorial. So essentially we're taking N factorial and then we're essentially canceling out the things that we don't need. So that N minus R factorial and the one we were just looking at would have resulted in the 23 factorial. We're essentially taking off that very last piece that we don't want. Such a list is called an arrangement. Because remember, technically this thing that I just wrote down is the number of such lists. But these are technically counting up how many lists of, you know, these elements in the certain order that we have. The P in the notation there is essentially reminding us that an arrangement is related to a permutation. So you'll probably hear me use permutation more often than arrangement because I'm more than permutations, but just know that they're somewhat interchangeable. There is a slight nuance between the two, but if I say permutation, I'm talking about an arrangement. If we want a permutation on a set, we use all of the elements in a set, which is why there's a slight nuance between arrangement and a permutation. So again, I shouldn't really use permutation all the time, but you'll probably hear me say it a lot. I'll try to say arrangement when I should. But anyway, if we want a permutation of a set, we use all the elements of a set. So how many permutations are there on a set of n elements? So how many actual full permutations? So using all of them. So essentially we'd want to calculate this once the one screen is lagging. I don't know which, the one screen's fine. The other one, there it is. So if we want an actual legit permutation, we would have to take all of those elements. Well, if we use this kind of relationship we just found, this would be n factorial over n minus n factorial. So we'd have n factorial over 0 factorial. Now 0 factorial is said to be 1, so this would be n factorial over 1, so n factorial. And if you think about it, if we have n elements and we're going to arrange them into a list, then we have n choices for the first one, n minus 1 choices for the second one, n minus 2 did I mess that up? N choices for the first one, n minus 1 choices for the second one, n minus 2 choices for the third one, and so on. So it does make sense that this should result in n factorial. Questions so far? So again, a permutation has to be on the entire set, and an arrangement can be on a, kind of subset of the set. So really, the main thing we're actually working with here is arrangements, but they're very related to permutations. Now, let's say that Margie is a caller for a bingo game, and there are 75 balls in the little bingo ball cage. And Margie draws 4 balls in sequence. So how many ways are there to do this if Margie gets distracted and accidentally replaces each ball in the cage after drawing the next one? So this one technically wouldn't quite be an arrangement necessarily, because we're replacing them each time. So essentially there's 75 balls. So if we have 4 balls that she's going to draw, well, you've got 75 choices for the first one. But then she got distracted and she put it back in, so there's still 75 choices for the second ball. And then she gets distracted and puts it back in, so there's still 75 for the third option and still 75 for the fourth option, respectively. So if she gets distracted and keeps replacing the ball each time, there's always 75 choices. Turns out to be 31,640,625 ways that can essentially happen. 75 to the fourth. But then what if we wanted to say, well, she's not distracted and she doesn't replace the balls back in? So now she starts with 75 balls, and every time she pulls one out, it stays out. So we still have 4, kind of spaces we have to fill. So there's 75 choices for the first one, essentially 74 for the second, because she didn't replace it back in. 73rd for the third, and 72 for the fourth. What am I writing? Good Lord. 72 for the fourth option. Now, if we think about this in terms of factorials, this could turn into 75 factorial. And then essentially we don't have 71 and backwards, so this would have to be divided by 71 factorial. So you can also think about this as essentially the arrangement of 75 objects into 4 spaces, which is essentially what that P of 75, 4 is saying. You're taking 75 things and you're taking 4 of them and arranging them. What does this actually turn out to be? I didn't actually calculate it. There it is. Whew. So wait, do I have too many numbers there? Do I not have enough numbers in the last one? Hold on. I have gone and confused myself. 3 1 4 0 6 2 5 2 9 1 7 0 8. Oh, I just put a comma in the wrong spot. I'm so dumb. 29,170,800. I was really confused why I was having 291 million when the original one was 31 million because I put a comma in the wrong spot. So obviously there should be less choices in this one because we're not replacing, so we don't have as many choices for each piece. Questions about... So that's essentially permutations. Arrangements is when you have a set of so many elements and you want to arrange them into a list of however many elements. So if you're viewing it as this kind of Pn of R notation, the n is the amount of elements that you have to choose from, and R is essentially how long your list is. So that's why this one we had 75 choices to choose from. The entire set had 75 elements in it. And then we were choosing 4 of them and arranging 4 of them into some specific order. Now, why is this not scrolling? Come on. Now, in that case, the order mattered, but sometimes the order doesn't matter. So say Ms. Baber needs 4 volunteers to do a job and offers her class extra credit. 12 students volunteer for the job, so to make things fair, Ms. Baber draws 4 names for a hat all at once. How many different ways are there to choose a group of 4 volunteers? So notice at this point, the order doesn't actually matter. If you have Bob, Joe, Laura, and Hope, it's the same as Joe, Hope, Laura, and Bob. You just need 4 people. They don't need to be in a specific order. So it's not going to be a full arrangement because in arrangements, the order matters. But in this case, it doesn't. So if we think about this, we have 12 candidates. And we want to choose 4 of them. So if we take the arrangement of 12 items into 4 pieces, that's going to count too many. So this overcounts, since order matters in arrangements. But if we could figure out kind of how much it overcounts, then we could just divide out by how many overcounted pieces there are. So essentially, if you think about, so how many times do we count the same group? Because again, if we have Bob, Joe, Laura, and Hope versus Joe, Hope, Laura, and Bob, those are going to be 2 completely different pieces in an arrangement. But here we want them to essentially be the same group, so we don't want to count that group twice. Well, if you think about it, we're essentially taking a group of 4 and arranging it into a set of 4. So essentially, if we take the set of arrangements on 4 objects into 4 spaces, this is going to essentially tell us how many times that group is counted. So you take 4 names, and if you arrange them, the order would matter. So you would take those 4 names and arrange them, which is this amount. And so what I've just said, I already said it. So that's essentially how many times we're going to count this same group is going to be the arrangement of 4 elements into 4 pieces. So we can find out what that is by either doing 4 factorial over 4 minus 4 factorial, or we already found that essentially the arrangement on n elements into n groups is just going to be n factorial. So this is going to be 4 factorial, which turns out to be 4 times 3 times 2 is 24. So essentially we're overcounting by 24 groups. So if we want to know how many ways there are actually to choose these 4 people, we can essentially say that it's the arrangement of 12 people into a set of 4 divided by essentially this set of 4 into 4, because that's how many we're overcounting. So we're essentially saying that the amount of times that the same group is counted is the arrangement of 4 elements into 4 pieces. So we're just going to divide out by that many pieces. Now I'm going to write this. I'm going to use the 4 factorial instead of 24. But if we think about what the arrangement of 12 elements into 4 groups is going to look like, that's going to look like 12 over 8 factorial, 12 minus 4. And then we're dividing by 4 factorial, which is what we found out to be P of 4 of 4. Now this is going to reduce to 12 factorial, that should be, over 8 factorial times 4 factorial. If you do a little algebra, dividing by 4 factorial will be the same as multiplying by 1 over 4 factorial, and then you kind of multiply the fractions together. So there's this many ways to choose. So essentially we take the arrangement, which turned out to be the 12 factorial divided by 8 factorial, but then we have to recognize that the arrangements are overcounting, and in this very specific situation they're overcounting by 4 factorial. So we have to divide that out. Does that make sense? Hopefully that made sense. Questions, concerns about that before I go to the definition of what this actually showed? Okay. So again, kind of what we were just looking at is we were looking at something that was unordered. We didn't care about, the order that we chose the people. So this type of choice is called a selection. You might hear me say combination. It's kind of similar to kind of the nuance between permutation and arrangement again. So again, I'll try to use selection, but if I say combination, this is what I'm talking about. So this is called a selection because again, an arrangement, it kind of makes sense because you arrange people in a certain order, but here you're just selecting people in a unordered way. So this leads to the selection principle. So the selection principle says that the number of ways to form an unordered list of R distinct elements drawn from a set of n elements is going to be kind of this C of n and R, which is n factorial over n minus R factorial times n factorial, which is kind of what we just looked at. We take essentially the arrangement, which is the n factorial time divided by n minus R factorial, but then we have to take out the amount that are being overcounted, and that's always going to be essentially Cn comma n, which turns out to be n factorial. Sorry. Let me write it in red so you know that I screwed up there. R factorial, not n factorial. Turned out to be n factorial in the last one. Sorry, R factorial, not n factorial, because then the n factorials would cancel each other out. Now this one is kind of nicer than the P of n comma R because there's actually a nice way to read it. These ones are read as n choose R. So you can actually read that as n choose R. So if it's C6 comma 4, that's 6 choose 4. So you can actually read those much nicer than the arrangement ones. Now there's also a different set of notation that we use for this sometimes. So if we have n choose R in that C notation, that can also be written like this. So it's essentially just parentheses and you have n and R. There's no division symbol in the middle. There's nothing like that. It's just n over R in some parentheses. So if you ever see something that looks like that, that's also n choose R. So if we have n elements and we only want to choose one thing, how many ways can we do that? Well, if we do n elements and we only choose one of them, we're going to have n factorial over n minus 1 all factorialed times 1 factorial. Now, if you think about the top, that's going to be n times n minus 1 factorial over n minus 1 factorial, and 1 factorial is just 1. So those n minus 1 factorials are going to cancel out. We're just going to get n. Now that makes complete sense. If you have n things and you just want to pick one of them, there are n ways to pick one thing. If you have 5 things and you're just picking one of them, there are 5 ways you could pick. What if we wanted to figure out what n choose n is? Well, if we figure it out using that formula we have n factorial over n minus n all factorial over n factorial. So we have n factorial over 0 factorial, n factorial. 0 factorial is 1, so n factorial over n factorial equals 1, which also makes sense if you have n elements and you want to choose all of them, and we don't care about the order in which you do so. There's only one way to do that. Now, if you cared about the order, there's of course way more ways to do that. But if you don't care about the order, if you're just taking all of the things, there's only one way to do that. Questions, concerns before we do some examples? Okay. Oops. So once again, arrangements, order matters, selections, it does not. Arrangements are related to permutations, selections are related to combinations. So let's go back to Margie and her bingo game, and there are still those 75 balls in her bingo ball cage. And she reaches in and draws a handful of 4 balls at once. How many different handfuls could Margie grab? So she reaches in, grabs 4. So she's not going to pull them out in a specific order. She's just going to pull all 4 of them out and look at all 4 of them at the same time. So it doesn't matter, you know, if it's 1, 2, 3, 4 versus 4, 3, 2, 1. We're not pulling them out in a very specific order. We're pulling all 4 of them out at once. So essentially we're choosing from 75 elements, we're choosing 4. So just to write it in the other kind of notation, 75 choose 4. So if we use our formula there, it's going to be n factorial, so 75 factorial, divided by n minus r factorial, so 75 minus 4 factorial. So what am I writing? Good Lord. Divided by r factorial, so 4. So we essentially have 75 factorial over 71 factorial, 4 factorial. So essentially, if I want to write this out, just a bit more generality before I write the final answer. Since we're essentially, we can kind of think about that 75 factorial divided by 71 factorial as kind of canceling out like we were looking at it when we were looking at arrangements. So the numerator can essentially reduce to 75 times 74 times 73 times 72. And then we would still have the 4 factorial in the denominator that we haven't canceled anything out with. This results in 1,215,450. So just taking the total of 75 balls, reaching in, grabbing 4 at once, there's over 1 million ways she could, you know, over 1 million different ways that she could grab those 4 balls out. Now, this next one is a bit more ambiguous, if you will. That's probably not the right word, but. So we want to look at how many solutions there are to the equation x sub 1 plus x sub 2 plus x sub 3 equals 11 if x sub 1, x sub 2, and x sub 3 are non-negative integers. So we're essentially just saying take 3 positive integers that add to 11. So you could even take 0 plus 0 plus 11. You could take 1 plus 1 plus 9. You could take, 5 plus 5 plus 1. Whatever floats your boat, as long as they're non-negative numbers. So how are we going to figure out how to do that in terms of these choices and permutations and selections and arrangements and all that jazz? Well, if you think about, like, almost as if we went all the way back to elementary school, and you know how in elementary school you always had those little manipulatives in math, like the little cubes, and then they turned into bigger blocks and stuff like that. Say we had like 11 sticks or 11, whatever. So if we kind of think about 11 in terms of 11 ones, so think of breaking 11 into 11 ones. And then essentially we can arrange those ones into kind of groups. So we can break that into groups. where essentially say you wanted to represent like 5 plus 2 plus, what would that have to be? Why is my brain not working? 4. That would be 1, 2, 3, 4, 5, and then say we do a larger thing for the separation. 1, 2, 1, 2, 3, 4. Or something like 3 plus 7 plus 1. We'd have 1, 2, 3 separated from 1, 2, 3, 4, 5, 6, 7 separated from 1. So if you think about this in terms of like spaces that I'm writing symbols in, if you will, I technically have 13 spaces. Spaces to fill here, where essentially 11 are the ones, I'm putting the ones in certain spots, and 2 of them are essentially those, separation pieces. We can kind of think of this as a plus sign. So you could almost think about it as, separating 5 plus 2 plus 4, 3 plus 7 plus 1. So if we think about that as breaking 11 into 11 ones and then breaking it up to a bunch of groups, we have essentially 13 spaces to fill. We have the 11 spaces for the little ones that we're putting down, and then we have 2 spaces for essentially where the ones are going to go. And so we essentially just need to fill those 13 spaces. So the way you can think about, so sense of rate, this isn't an arrangement. This is going to be a selection because the order is not going to matter. Okay, so 5 plus 2 plus 4 is going to be the same as 4 plus 2 plus 5, so we can just rearrange them. So essentially what you want to think of is think of placing the plus signs. So I'm going to move them over to plus signs instead of trying to do that thick line each time. So essentially, if we say that we get to choose where the plus signs are and then everything else just gets filled in with a 1, that'll tell us how many ways we can do this. So essentially we have 13 spaces and we're going to choose 2 spaces to put the plus signs in. And it's perfectly okay if the plus sign is in the very first or the very last place, because then we essentially just have a 0. So if the plus sign is in the very first spot, then one of the numbers is 0. So we essentially can think of this as choosing between those 13 spaces, we're going to choose where to put those 2 plus signs. And that is actually going to tell us how many arrangements we're going to, well, I should be careful, how many ways we can do this. Because if we just choose where to put the plus signs, everything else has to fall into place. So that turns out to the calculation of 13 factorial over 11 factorial times 2 factorial. The 11 coming from 13 minus 2, which is 78. So there's essentially 78 different solutions to x sub 1 plus x sub 2 plus x sub 3. And we could thought about that as breaking that 11 up into 1 pieces, into 11 ones. And then we essentially have 13 spaces to fill. We have the 11 ones to put down, and then we have 2 plus signs. We just think about placing the plus signs down and everything else has to be forced into a 1. We can think about it as the amount of equations, the amount of solutions is going to be 13, choose 2. You choose where to put the 2 plus signs. Questions, concerns about that one? Again, as I said, that one was a little more ambiguous than the other ones we were doing. Wait a couple more seconds just in case. Okay. So, next one then, which is going back to something the tiniest bit more concrete. I should be careful with the word concrete, but so to advance to the Stanley Cup playoffs, the team must win a best of 7 match. Suppose the Los Angeles Kings are going to face the. I think so. I swear there is. Am I crazy? There it is. let me actually show you all that. There's actually, I was going to try to avoid showing you that there's a way to also do the permutation and combination ones, but you're going to see it when I show you how to do the factorial, so. But you still want to know how to write it down in terms of the factorials because I'll expect you to write it down like that. But give me 1 second. I'm trying to pull up my little calculator doodad here to show you how to do that. If you have not a TI, you'll have to Google it. But why isn't it letting me share the thing? Okay, we'll just do this then. Here we go. Okay, so if you have a TI-84 or it should also work on an 83, the notation might look a little bit different. If you don't have a TI-83 or 84, you might have to Google it. If you have Inspire, I can probably figure it out, but because I have an Inspire, but I've never actually looked at how to do it on an Inspire. Sorry, I'm looking at it right now. I'll have to figure that out later. So if you have a TI-83 or 84, if you hit the math button, well, let me put 9 first. Maybe I'm going to figure out 9 factorial. So you'll hit math, and then you'll want to scroll over to the probability one. So you can just kind of press the over button to get over to the probability one. And if you have a newer calculator, it should just be the factorial symbol. If it's an older one, I'm not exactly sure what it would show, but it should be option 4 no matter what. So notice that there's also these two above are technically the calculations for the arrangements and the combinations. So I can show you how that'll work in a second, but you still need to know how to write them down. So 9 factorial. Notice though, be careful though, because the factorial will overload the calculator very quickly. So like if I wanted to do, let me see how fast it overloads. Okay, well that's already writing in scientific notation. And I'm pretty sure if I go up to maybe 21. Oh no, interesting. About 50, that probably overloads it. No? Okay, well maybe I'm crazy. I think eventually it does overload. Unless the calculators have gotten much better than I think they are. There we go. Okay. So know that sometimes the factorials get too large and it can't do it. So that's another reason to be used to working with them a little bit by hand at least. Like in that one where we were doing Margie with her bingo game and we had 75 factorial over 71 factorial times 4 factorial. Realizing that you can essentially cancel out parts of the 75 factorial and the 71 factorial is really good for them trying to put it into your calculator. Now, if you want to do those, other ones, you would have to put in the number first, go over to it, and say we wanted the arrangement on, let's see if it can calculate 75. Wait, no, am I doing this wrong? I think I put it in backwards. So say I want to do choosing 4 elements on 75. I think I have to put the 75 in first. Let's see if it can do this. Yeah, because N has to come first and then R. So it's a little bit different notation. But yeah, there we go. So that's actually the one we just did in example 13, 75, choose 4. So yes, your calculator can do it. Yes, I still expect you to know how to write it out. But your calculator can find you the thing, whatever. Anyway, does anyone have a TI Inspire? Really quick, give me a yes or no or raise your hand or something. Because I can probably figure it out kind of quickly if you have one. Oh, I found it! Well, no one says they have one, so never mind. So that's how you do factorials and combinations and permutations. Sorry, my laptop is not working. Come on, go back to the notes. Oh no. Please go back to the notes. Oh no. Oh. Now it doesn't give me the option. So I'll just do it this way. Oh my God. Why will you expect the complete number as a final answer? Will the final notation before calculating it be acceptable? The notation will probably be fine because essentially I'm going to want to see the notation anyway. So I feel like I'd be completely fine if you just stopped with the notation and just didn't write down the final number. If you wrote down the final number but didn't have the notation, that'd be bad news bear. Because I want to see the notation. But no, I think if you stopped at the notation, like if you were on this one and you just did, well, so I want to be careful with what I classify as notation. I'm talking about the factorial step. So writing 13 choose 2 wouldn't be enough. You'd want to write it in the factorial way. But if you didn't write down 78, it wouldn't be the end of the world. So there's that. I want to slightly careful because I might change my mind on that on the final because the final's online. And so since the final's online, I might just have a space for the actual final answer, but I'll talk about that more when what I'm doing for the final. And the final is going to be open note, open whatever, so you could always jump on a online calculator and have it calculated for you if you were doing the final. But yeah, in terms of this next exam, that factorial thing would be fine. Anyway. All right, so let's do, this is probably the last one we're going to get to. Now, since I steal these notes, I don't know if this is an actual sports thing or not. So don't come at me if that's not actual sports things, because I don't know sports. But anyway, so say we're saying to advance to the Stanley Cup playoffs, the team must win a best-of-7 match. Los Angeles Kings are going to face the Chicago Blackhawks in playoffs. How many different win-loss scenarios are there? So this almost goes back to the idea that we started with today, where kind of we have a multiplication principle and then an addition principle, but it's more of a choose situation. So to advance, a team must win, 4 games. There's 7 matches. The best of 7 is 4. So they could win either there could be 4, 5, 6, or 7 matches. They could win the first 4 and be done. They could lose one of the first 4 and have to play a 5th, and so on and so forth. So there could be either 4, 5, 6, or 7 games before either team actually gets to 4 wins. So that's how we're kind of going to break it up. We're going to break it up into kind of those disjoint cases, 4 total games, 5 total games, 6 total games, or 7 total games. And then we're going to find the amount of ways that they can do that. And then we're going to add all of those options together. So we need to be a little careful with the space here because, well, if you're writing it on this paper, I guess if you're writing it on generic paper, you have as much as you want. So say we're doing 4 games total. We just kind of space this out so I don't run out of space. 6 games total and 7 games total. So the 4 games total. So now remember, we have 2 different teams, and we have to take into consideration the fact that either one of them could advance. So essentially, the games could be that the Los Angeles Kings win. So let me maybe do LA, 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 LA. So they could win all 4 of the first ones. Or the Chicago Blackhawks could win the first 4. So like it could go either way. So technically in this case, so essentially the advancing team loses 0 games in the first 4 games. And essentially, let me write this in a different color so it kind of stands out. There's 2 ways to do that. Either the Los Angeles Kings win all of them or the Chicago Blackhawks win all of them. So there's kind of 2 ways that we could have only 4 games before moving forward. If we have 5 games, you know, for example, you could have that Chicago wins 2 of them and then LA wins the 3rd one. So then Chicago has to win the next 2. There's of course a lot of different, you know, ways you could arrange that. LA could win the first one and then Chicago could win the other 4. But for example, so essentially what's going to happen is the advancing team loses 1 game in the first 4. You know, the loss has to come within the first 4 games or else, you know, someone has won 4 games. So the advancing team, we're going to think about it as, we're going to phrase these in terms of the advancing team losing to figure out how many cases there are. So the advancing team would have to lose 1 game in the first 4 games in order for there to be a 5th one, assuming that they then went on and win the 5th one. So essentially, if we think about like the Kings advancing, we essentially have 4 choose 1. They essentially choose which game they lose. Do they lose the first one? Do they lose the second one? Do they lose the 3rd one? Or do they lose the 4th one? Again, if they advance, they aren't going to lose the 5th one, and so on and so forth. So there's essentially 4 choose 1 ways for them to lose one of the first 4 games. So there's 4 ways to do that. But then if the Blackhawks advance, it's essentially the same deal. Well, they have 4 choose 1 ways of losing one of the first 4 games, so there's 4 ways to do that. So in the case of having 5 games, there's 8 ways for that to happen. And it's always in terms of, if we think about it in terms of the advancing team, how many must they lose? To play 5 games total, there should only be 1 loss. And it has to be a loss in one of the first 4 games, so it's 4 choose 1. If we're looking at a total of 6 games, so I'm not going to write it on an example for that, but essentially they must lose 2 within the first 5 games. So again, they can't lose the last game because then the arrangement would have been that they won 5 games in there beforehand. So they must, so essentially the advancing team loses 2 games within the first 5. Now, how many ways to do that? Now, to save myself a little bit of space, we have the option of the Kings advancing and then the Blackhawks advancing, but they're going to come out to the same number in each case. I'm just going to take the kind of choose calculation and multiply it by 2, okay? So we essentially have 2 ways for this to happen, either the Kings or the Blackhawks. And in this case, we have 5 games and we're choosing to lose, we're essentially choosing which 2 of them are losses. So we have essentially 5 choose 2. Which 2 are the losses? And those choices essentially give us the selection for those options. This is going to be 2 times 10. Maybe I should, let me write out the factorial way. So it would be 5 factorial over 3 factorial times 2 factorial, which will be 10. So 2 times 10 is, let me write it in another color again so it pops out. So we have 20 ways for there to be only 6 games. And then very similarly with the 7 games, again, they can't lose the last one because then they would have won 6 games and it would have been a 6-game situation. So they essentially have to lose 3 games within the first 6. So the advancing team would advancing team loses 3 games within first 6 games. What the heck? Now again, there's 2 teams that could advance, so there's kind of 2 options. But then if we essentially think about it as choosing the games that are lost, we're essentially doing 6 choose 3. So 2 times 6 factorial over 3 factorial times 3 factorial. So 6 times 3 gives me the first 3, and then the other 3 just comes from the r factorial. That's going to be 20. So I guess in this case, Dakota, you would have to find the actual final answer. So I guess it also depends on the question that I ask you. But if it was one like the last one where the number, you didn't really have to do anything with it, then it was fine. But here we have to do something with all of the numbers, so we need them all. So essentially, now we have these disjoint situations. We either have they win 4 games, they win 5, they have 4 games, 5 games, 6 games, or 7 games. So the total amount of ways that this could happen. So again, since they're all disjoint, we can essentially go back to that addition principle and say we have 2 ways plus 8 ways plus 20 ways plus 40 ways. So there are 70 total scenarios. Questions, concerns on that one? Okay. So the next thing we have to talk about is now if you printed out these notes a little while ago, so Dakota, essentially it's like, yes, and the reason being, so if we say like LA wins the first 4 games, it doesn't have to be, we don't have to list it as game 1, game 2, game 3, game 4, or game 4, game 3, game 2, game 1. So like an arrangement would count like the order of the games. We don't really care about the order of the games. We just care that they won 4 games. We don't care about listing them in their correct order. So yeah, here it's not an arrangement because so I know obviously they're going to play the games in an order, but when we're just listing them in terms of figuring out how many there are, we don't need to list them in a correct order. So we don't need an order here, so it's a selection, not an arrangement. So the next thing we need to talk about, and again, if you printed these, if you even print these notes out, if you found these notes before like an hour before class, it wouldn't have had this very nice picture in it. So the next thing we have to talk about is, why is that one red? Oopsies. Anyway, the next thing we have to talk about is somewhat tedious because I have to talk about this thing. So I think I'm gonna hold off on that for what's it called, Thursday, and just let us go a little bit early. So in terms of your quiz on Thursday, it's gonna be on 4.1 and 4.2. So multiplication, addition principle, permutations and combinations, arrangements and selections. Goodness gracious. It will be not quite as in depth as this last one. It'll be not as ambiguous as that one. It'll be a bit more like these Margie Bingo examples, or possibly even this example 4, except you wouldn't have to write out all the hoopla. You would just have to find that it's 12 choose 4. And of course with the permutations, arrangements. Again, sorry, I'm so used to calling them permutations. So it's more like some of those beginning examples and the examples from 4.1 than those last examples that we talked over. But that's essentially what it'll be. I'll give you a situation and ask you to find either a selection or an arrangement of a certain amount of numbers over a certain set of whatever. And again, in terms of the quiz, writing it in these factorials will be fine. You can leave it there if you want. If you want to find the actual number, that's perfectly fine. I will need you to show the factorial statement, though. Like, I don't want you to just punch it in your calculator because I just showed you how to do that. I don't care that your calculator knows how to do it. I care that you know how to set it up. So I will need to see the factorial notation, but you can also find the final answer if you want to. But that's what your quiz will be on Thursday. Let me write it in chat so that you can go and find it later if you want to. If you guys even realize that that was an option. That's why I write it in chat, so you can always go find it later. So multiplication, addition principle, and arrangements and selections on a, I'm gonna write simple situation. And again, that's just me trying to say, like, it's not quite like that last one that we did where we had to do a ton of different options, and it's not quite as ambiguous as that how many solutions one that we talked about. Oops. But it will be on that type of stuff. So I know we're a little bit early, but it's not worth going over the big hoopla that we're going to talk about next. So I'll let you go. If you have any questions, feel free to stick around for a little bit. Otherwise, have a good day. I'll see you on Thursday. I'm going to stop recording now.